Today we're going to continue on. This topic is arguably the most applicable, the most everyday life, the most useful part of the unit. So as a quick do now to get you started, just take a look at this. This should be very reminiscent of the last lesson you had. Just take a second. I added a slight tweak to it. Identify the acids, just the acids, in either side of the equation. Even though there are sodium ions present, remember that sodium compounds are always soluble in water, so it's almost like the sodium ions can be ignored, or a spectator, if you will. It's more important to look at the hydrogen ions and what they are. This substance has one hydrogen, this substance has one, this substance is 0 afterwards, and this has 2. So clearly a hydrogen moved that way. That would make this the acid. And then working in the reverse direction, it would move that way. So that makes this the acid. This is an image you can find on Google. It's an image you can find in a textbook. There are all these scales of the pH and whether or not something is an acid or a base or acidic or alkaline. But hopefully just even looking at this and thinking about it for a second, your brain should go, wait a second. But what is pH? How is it measured? How does it actually relate to acidity? And that's what we're going to take a look at today. Most of these substances are kind of fixed, but I think the biggest misconception that people have about pH is that, yes, bleach has a pH of 13. No, it doesn't. The bleach that you buy in a store comes at a certain concentration, and that concentration will yield a pH value of about 13. Same thing with like stomach acid. The contents of your stomach change over time. If you drink water, the concentration of what's in your stomach changes, and then the pH of your stomach contents change. By drinking water, I've shifted the pH slightly. So you can't just say, stomach acid is a 1. To get into pH, though, I think the first thing to consider is in any sample of water, you have your beaker, and there's lots and lots of H2Os, all these H2O particles. We established in our previous lesson that water has the propensity to act as an acid or a base. What we see is that there is a chance that two water particles can collide with sufficient energy and sufficient orientation to have one of them act as a base and one of them act as an acid. This is in equilibrium because obviously those two particles could then recollide and then they could recreate the waters, and so this is constantly happening. But if this is an equilibrium and it's constantly happening, that means there's a constant concentration. So if we can figure out that constant concentration, that might yield some information. It's really more fair to say that in every sample of water, there is some H3O plus and some OH minus. But how much? There's a way to measure the amount present at equilibrium. It involves something called an equilibrium constant, and I'll just give you the one for water because it's an important one. It is always true for any aqueous solution, which all of these are aqueous solutions. As long as there's water present, this equilibrium is taking place, and for all water, the concentration of H3O plus times the concentration of hydroxide is always equal to 1 times 10 to the negative 14th. Some of your textbooks will refer to this as Kw, constant for water. Remember that this is also H plus times OH minus is equal to 1 times 10 to the negative 14th. If you were considering pure water, based on the chemistry of this equation, the number, the concentration of hydronium and the concentration of hydroxide have to be equal. Conservation of matter says if you create one hydronium, you have to create one hydroxide. One H plus moves from one water to another, you create one of each particle. Well, that means if we're in pure water, we can say they're equal to each other. And if we wanted to, we could just call that, say, X. In other words, X squared equals 1 times 10 to the negative 14th, and then X equals 1 times 10 to the negative 7th molar, which is 0.0001 molar. It's a small number. I'm not equating this to a parts per million or anything like that, but roughly that's 1 in 10 million. So at equilibrium, for every 10 million water molecules, you have one hydronium. which is not a terribly large number. The solution is vastly, vastly water and nothing else. But this number is very important, and I'm sure some of you are looking at this going, wait, there's a 14 there, and there's a 14. That's super important. Before we get into measuring pH of acids, I wanted to take a second to talk about logarithms. Of course, everyone's at a different point in their math classes, but some of you are taking trig, some of you are not taking trig. I just wanted to fill in the blanks. So a logarithm is a function, which means plug in one number, perform function, get out other number. So I have 4 different numbers and their logarithms. Hopefully we can see the pattern. Think about it for a second. Try and figure out the pattern between what happens to x and what happens to the log of x. You can probably see this, right? This is a change of times 10, and this is a change of plus 1. This is a change of times 100, and this is a change of plus 2. It's a function. For most situations, you can just think of it as a button on your calculator, and it performs the function for you. In simple definitions, a logarithm is what power do you raise 10 to get x? In other words, 10 to the 0.555 power equals 3.59. It's just another way of writing this exponent in a way where you're kind of starting with the answer instead of starting with the exponent. This relationship is really important, where a logarithm works by taking your input values, and for every power of 10, you only see a difference of 1 unit. So it really condenses down massive changes. And the reason I say that is that the function p is an operator. Lowercase p in chemistry, elsewhere, means negative log of. Px equals negative log of x. Yeah, it's possible to measure the log of a different base. We use base 10 especially for the p operator. Looking at the same x values for the first 2 columns, we notice that if the x value gets 10 times larger, the px value decreases by 1. If the x value gets 10 times smaller, the p value increases by 1. And the reason you see that is because there's this negative here. You can also compare here. If the x value gets 100 times smaller, the p value gets increased by 2. So for every power of 10, it's 1 unit. You can apply the function p to anything, and in chemistry we do this because, especially when you have really small concentrations, it helps our brain understand what we're looking at. So you can measure the p of anything. So pH would be negative log of the H plus concentration. You could also measure, if you wanted, pOH or pNa or pCl, I don't know, whatever you want. And there's probably reasons that people would look at each of these, but in terms of acids and bases, measuring the pH is a natural progression. Let's look at some solutions. First, let's take HCl, our standard hydrochloric acid solution. We want to figure out the pH of a 0.100 molar solution. The first question I have to ask is, well, what is the H plus concentration? We know that hydrochloric acid will react with water in a one-way reaction to make H3O plus Cl minus. In a 0.100 molar solution, this doesn't really exist because it's a one-way process, and that means that this concentration is 0.100 molar and 0.100 molar. I think we've talked about this with moles in general. 1 mole of sodium chloride contains 1 mole of sodium and 1 mole of chloride. So a 0.1 molar solution of HCl would be 0.1 molar H plus and 0.1 molar Cl minus. So in this solution, the hydronium ion concentration is 0.100 molar. Don't forget, we had this reaction. Equilibrium already exists. That's what water does. So if you add the HCl, and that increases the H plus concentration. Well, that's a stress. If we increase H plus, what's going to happen is you'll see a shift left. And what will happen is, yeah, this will go down, but more importantly, the hydroxide will go down. Now, this is where I'm going to try and avoid a lot of the math. It would probably invoke a quadratic equation. I don't want to do that. Let's just say that the decrease in the H plus concentration is negligible. As H plus increases, OH minus concentration decreases, and we know that because it always has to multiply to equal 1 times 10 to the minus 14th. To find the pH of the solution, all you have to do is negative log of 0.100. And if you grab your calculator, you calculate that, what you get is 1. I will show how that gets a little bit simpler to manipulate, but that's our answer right there. Now, if we wanted to figure out the pH of a base, this seems a little bit counterintuitive because we know that sodium hydroxide will dissolve to make Na plus OH minus. If we wanted to figure out the pH, how do we figure out the pH when there's no H? I don't see any H's, I see hydroxides, but I don't see any H pluses. Well, the easiest way to figure out pH, as long as you don't forget that this is aqueous, there is water present. And the presence of the hydroxide, just like we saw on the previous slide, the presence of the hydroxide impacts the hydronium, just like the presence of the hydronium affects the hydroxide. In a 0.010 molar solution of sodium hydroxide, that the hydroxide ion concentration is 0.010 molar. We also know that because there's water present, the product of the H plus and the OH minus concentrations always has to be 1 times 10 to the minus 14th. Now we said before for pure water, H plus and OH minus are equal because of stoichiometry. Here, it's not pure water. There's a lot more hydroxide. We now know that not only are they not equal, we know what one of them is. Equals H plus times 0.010. H plus is equal to 1 times 10 to the negative 12th. Plug that into your calculator. pH equals the negative log of 1 times 10 to the negative 12th, which is equal to 12. Now this is consistent with what we know about bases. We said that the pH of bases is greater than 7. Now this is weird because this suggests that even in a basic solution, there is still H plus present. And so there's a bunch of conclusions we can draw about that. We know for neutral that the concentration of H plus equals the concentration of OH minus. And we know in acidic solutions, all that really means is that the concentration of H plus is greater than the concentration of OH minus. As you add an acid to water, the hydronium goes up, and because of equilibrium, the hydroxide goes down. And in an alkaline solution, that doesn't mean just hydroxide. All that means is that the H plus concentration is less than the hydroxide ion concentration. You add base, the hydroxide ion concentration goes up, the hydronium concentration goes down. We also know that if the H plus ion concentration goes up, right, they were equal, now H plus is greater, that also means that the pH is going down. If the pH goes up, that means that the H plus concentration goes down. As the X value goes up, the pX value goes down. As the X value goes down, the pX value goes up. I don't know if you noticed this on the previous slide, but there's a little pattern that I noticed I wanted to show. Some other people will refer to pH as the power of hydrogen or the potential of hydrogen. Since it's based on logarithms, logarithms are directly related to powers of 10. We see that pH is the negative log of the H plus concentration. You can rewrite that to be 10 to the negative pH equals H plus. If the concentration of H plus is equal to 1 times 10 to the negative x, pH equals x. We see when you perform the p value, like the p function on non-1 values. This is not 1 times 10 to something, it's 3.59. The pH, the px, is not a whole number, and that's okay, but you can still use that application here to convert back to your H plus concentration. If H plus is equal to 1 times 10 to the negative third molar, pH equals 3. If it's 1 times 10 to the negative fourth molar, pH equals 4. If the H plus was 2 times 10 to the negative third molar, I would guess that the pH is in between 3 and 4. You can also relate pH and pOH. This equation that we wrote here, if you perform some logarithmic magic to it, you get this. And this would be a potentially much faster way to solve the previous problem. If the hydroxide ion concentration is 0.01 molar, this also means that you could convert this to a pOH of 2. And if pOH is 2, and pH plus pOH is always 14, or everything we said about pH is also true of pOH. There's all these like seesaw-like relationships going on. So just to sum things up, pH equals the negative log of the H plus ion concentration. The H plus concentration times the OH minus concentration equals 1 times 10 to the negative 14th. As H plus goes up, pH goes down, and then there's a bunch of relationships that come out of that. There's a couple more things I want to say about a summary. The initial picture I showed you showed a scale from 0 to 14. That's really a boundary. It's not a hard boundary. It's a boundary for like biological systems. But I know that concentrated hydrochloric acid, the maximum saturated, is 12 molar. So hypothetically, you can make a 10 molar HCl solution. And that means that you would have 10 molar H plus. So the negative log of 10 equals negative 1. So your pH would be negative 1. It is possible to have negative pHs. It's possible to have pHs above 14. It just really needs really high concentrations of either acid or base. You could have a pH of negative 2, but that would be a 100 molar HCl solution, which can't happen. For each pH unit change, H plus changes 10 times. 2 becomes 100 times, 3 becomes 1,000 times. And I think I just wrote behind my own head. But if we combine this statement and this statement, we can kind of make statements about any solution. Thanks for watching.